Please pause the video and try this problem. Now let's discuss the problem together. Remember, if you find that these video explanations move too slowly, you can simply try the problems in the Problems document, study the solutions in the Solutions documents, and, if necessary, use the table of contents for each video to skip to the particular parts of the videos that cover the parts of the solutions that are giving you difficulty. Here are some keyboard shortcuts which you may find useful while you're watching the videos. Here's a summary of the solution to the problem, and now let's discuss the solution step by step. This question asks us for the difference in height of the two masses, 1.5 seconds after they are released. Because object 2 is more massive than object 1, common sense tells us that when they are released, object 2 will fall downwards, which will drag object 1 upwards. So, we draw V2 pointing down and V1 pointing up to indicate the object's directions of motion after they are released. The problem uses units of kilograms and seconds, and yes, those are both SI units. The problem refers to the concept of mass, which fits into a Newton's second law problem-solving framework. The problem also refers to the concept of time and to the difference in height, which is a type of distance. Time and distance do not fit easily into the Newton's second law equations. Instead, time and distance fit into the kinematics problem-solving framework. So, we expect to use both the Newton's second law problem-solving framework and the kinematics framework to solve this problem. Now, what type of kinematics will we apply? We can use the term general kinematics to indicate that we are not applying projectile motion for this problem. We will use one-dimensional kinematics because each mass is moving in a straight line. Which of these frameworks should we apply first for this problem? Well, the question asks us for the difference in heights, which is a kinematics-related concept. That implies that we should begin by applying Newton's second law, and then apply kinematics to answer the question. What is the connecting link between Newton's second law and kinematics? The one concept that appears in both the Newton's second law equations and the kinematics equations is acceleration. So, acceleration is the connecting link between Newton's second law and kinematics. Think in terms of components. The masses are moving in the y component, so we plan to apply kinematics to the y component. So the connecting links for this problem will be a sub 1 y and a sub 2 y. So our plan is to begin with Newton's second law. We will use Newton's second law to find a sub 1 y and a sub 2 y. Then we can substitute our result for a1y or a2y into the kinematics framework. Then we can use kinematics to answer the question. Remember, we used the concepts that were mentioned in the problem to determine that we would require both Newton's second law and kinematics to solve this problem. Now let's discuss the free body diagrams. We usually draw a free body diagram for each object whose mass is mentioned in the problem. So for this problem, we draw two separate free body diagrams. One diagram showing all the forces being exerted on mass 1, and a separate diagram showing all the forces being exerted on mass 2. Let's begin with the free body diagram for mass 1. We begin by drawing the weight force on mass 1. To complete the free body diagram for mass 1, we ask what is touching mass 1. Mass 1 is being touched by the rope, which exerts a tension force on mass 1. Are there any other forces on mass 1? Well, ask yourself, is there anything else that is touching mass 1 besides the rope? No, nothing else is touching mass 1, so there are no other forces on mass 1. Now let's work on the free body diagram for mass 2. We begin by drawing the weight force on mass 2. We use 1 and 2 subscripts to distinguish the weight force exerted on mass 1 from the weight force exerted on mass 2. To complete the free body diagram for mass 2, we ask what is touching mass 2. Mass 2 is being touched by the rope. The rope will exert a tension force on mass 2. We use 1 and 2 subscripts to carefully distinguish the tension force exerted on mass 1 from the tension force exerted on mass 2. Are there any other forces on mass 2? Well, ask yourself, is there anything else that is touching mass 2 besides the rope? No, nothing else is touching mass 2, so there are no other forces on mass 2. Now let's discuss the directions of the forces. The weight force always points straight down. The tension force exerted by the rope on mass 1 points parallel to the rope and away from mass 1. So the tension force exerted on mass 1 points up. The tension force exerted by the rope on mass 2 points parallel to the rope and away from mass 2. So the tension force exerted by the rope on mass 2 also points up. Now let's discuss the force tables. We need a force table for mass 1 and a force table for mass 2. The purpose of the first row of the force table is to represent the magnitudes of the force vectors. We use the special formula W equals mg to calculate the magnitude of the weight force on mass 1 and the magnitude of the weight force on mass 2. There is no special formula for the magnitude of the tension force, so we will represent the unknown magnitude of the tension force with a symbol. For a massless rope stretched over a massless frictionless pulley, the magnitude of the tension force is the same at both ends of the rope. Now, this problem doesn't explicitly say that the pulley is frictionless, but in an introductory course, we can assume that the pulley is frictionless, unless the problem indicates otherwise. So, the magnitude of the tension force exerted on mass 1 will be the same as the magnitude of the tension force exerted on mass 2. So, we can use the same symbol, capital T, written without an arrow on top, to stand for the magnitude of the tension force exerted on mass 1 and for the magnitude of the tension force exerted on mass 2 in the first row of our force tables. Before we can break the forces into components, we must choose our axes for each object. As a beginning physics student, for multiple object problems, I recommend that you should choose the direction of motion for each object as the positive direction for that object. We decided earlier that because object 2 has a greater mass than object 1, object 2 will fall downwards, and object 1 will be dragged upwards. Mass 1 is moving up. So for mass 1, we choose a y-axis that points up, and let's choose an x-axis that points to the right. Mass 2 is moving down. So, for mass 2, we choose a positive y-axis that points down. It's okay to choose different axes for different objects. Now, some professors might prefer to choose up as the positive y direction for mass 2, but in my opinion, that would be an inferior approach for most beginning physics students. Always write down your axes for each object. Now that we've chosen our axes, we're ready to break the forces into components. For this problem, we can use this rule to break all of the forces into components. For mass 1, we chose up as the positive y direction and down as the negative y direction. So for mass 1, the tension force points in the positive y direction, and the weight force points in the negative y direction. So for mass 1, T sub y is positive, and W sub y is negative. But remember that we chose a different y-axis for mass 2 than for mass 1. For mass 2, we chose down as the positive y direction and up as the negative y direction. So, for mass 2, the tension force points in the negative y direction, and the weight force points in the positive y direction. So, for mass 2, T sub y is negative, and for mass 2, W sub y is positive. Include a plus sign in front of all positive components, because that will help you to remember to include the crucial negative signs in front of the negative components. It's crucial to get every sign correct for every component in your force table. If you get any of these signs incorrect, you will get the wrong answer to the problem. Now we're ready to work with the Newton's second law equations. First, write the general Newton's second law equations. In this problem, the masses experience forces only in the y component. There are no forces in the x component. So, we write the Newton's second law equations only for the y component. For this problem, there's no need to write the Newton's second law equations for the x component. Now we can plug specifics into the equations. If you choose a positive direction for each object that points in the direction of motion for that object, then the acceleration component in the component of motion for one object will equal the acceleration component in the component of motion for the other object. We've chosen a positive y-axis for mass 1 that points up, which is the direction of motion for mass 1. And we've chosen a positive y-axis for mass 2 that points down, which is the direction of motion for mass 2. So, the axes that we've chosen do satisfy this requirement. So, we can write the equation a sub 1y equals a sub 2y. Then we can use that equation to substitute a1y in for a2y in the Newton's second law equation for mass 2. We can continue to use the symbol a1y in the Newton's second law equation for mass 1. Remember, this rule only works if you choose a positive direction for each object that points in the direction of motion for that object. For example, if you choose up as your positive y direction for mass 2, then a1y will not equal a2y. So, as a beginning physics student, you will make your life easier for multiple object problems if you make it a habit to choose a positive direction for each object that points in the direction of motion for that object. Now we're ready to solve the Newton's second law equations. When we consider these two equations together, they form a system of two simultaneous equations with a total of two unknowns, capital T and a sub 1y. When you have as many equations as unknowns, it's usually possible to solve for the unknowns. The most efficient way to solve this particular system of equations is the addition method. We take the Newton's second law y equation for mass 1 and we rewrite that equation underneath the y equation for mass 2. When we add the two equations, the t's cancel out. That's the reason why the addition method was an efficient method for solving these particular equations. Now we have an equation in one unknown, so we can solve this equation for a1y. Our result is that a1y equals positive 2.45 meters per second squared. Because of this equation, we know that a2y also equals positive 2.45 meters per second squared. To determine t, we can substitute our result for a1y into the Newton's second law y equation for mass 1. Now, for this problem, we don't need to know the value of t in order to answer the question, but I'm going to determine t anyway, because knowing the value for t could help us to check whether our results make sense. We've used the Newton's second law equations to determine a1y and a2y. Next, according to our initial plan, we need to apply kinematics in order to finish solving the problem. Here and here is the work that we will do to apply kinematics to this problem. And now let's discuss the kinematics process step by step. Here's a handout which contains a step-by-step method for applying general, one-dimensional kinematics. There's a link to this handout in the video description box. You should print out this handout so that you can follow along with the steps as we proceed through the video. If you thought that the kinematics portion of this problem was easy, then maybe you don't need to be this systematic. But if you thought that the kinematics for this problem was challenging, then I encourage you to follow this step-by-step kinematics process. There are two types of kinematics in an introductory course: constant velocity kinematics and kinematics with constant acceleration and changing velocity. Which type of kinematics applies to this problem? In this problem, the masses begin at rest and then start moving. That means that each mass's velocity changes. So the velocity is changing, not constant. Is the acceleration constant? The acceleration is determined by the net force. The forces we identified in our force tables are all constant. Since the forces are all constant, the net force on each object is constant. Since the net force is constant, we know that the acceleration is constant. So, for this problem, we will apply kinematics with constant acceleration and changing velocity. For a kinematics problem, we should build as much kinematics information as possible into our sketch. This problem asks us to compare the final heights of both masses. So for this problem, we will build kinematics information about both of the masses into our sketch. I will use this arrow and this arrow to indicate that the object's paths of motion are from here to here and from here to here. Let's call the moment when the masses are released t sub 0. We will make the standard simplifying assumption that t sub 0 equals the number 0. Let's call the moment when 1.5 seconds have elapsed t sub 1. If t sub 0 equals 0, then t sub 1 equals 1.5 seconds. The initial and final points are defined as the 2 points that we will substitute into our kinematics equation. For this problem, we plan to substitute t sub 0 and t sub 1 into our kinematics equation. So we should label t sub 0 as the initial point and t sub 1 as the final point in our sketch. Most general one-dimensional kinematics problems involve an object that either begins or ends at rest. This problem says that the masses are held and then released. That wording implies that the masses begin moving from rest. Because the masses begin from rest, we know that v sub 0y equals 0 for both masses. Build that information into your sketch. Think in terms of components. The objects are moving in the y component. So we plan to apply kinematics to the y component. So we focus specifically on the kinematics variable for the y component, v sub 0, y. This symbol stands for the y component of the velocity at time 0. When possible, build the question into the sketch. This question asks us for the difference in height after 1.5 seconds. We can build that question into the sketch like so. For a kinematics problem, we should build as much kinematics information as possible into our sketch. Here are the steps we've completed so far in our kinematics process. Next, we write down our kinematics setup. For constant acceleration with changing velocity, the kinematics setup consists of simply listing the 5 kinematics variables, like this. The objects are moving only in the y component, so we will be applying kinematics only to the y component. So we write down the kinematics variables specifically for the y component. Delta t, delta y, v initial y, v final y, and a sub y. We use the symbol delta y rather than the symbol delta x, and we use y subscripts for the velocity and acceleration variables. Because they're connected by the rope, both masses will travel the same distance. So we only need to apply a kinematics equation to one of the two objects, say mass 1. Next, underneath our list of the general kinematics variables, we list the specific numbers and symbols that apply for this problem. The problem tells us that the time that elapses, delta t, is 1.5 seconds. The symbol delta y stands for the y component of the displacement. In order to determine the final difference in heights, we will need to find delta y. We write the word need to indicate that delta y is the kinematics variable that we need to figure out in order to answer the question. In our kinematics equation, we will continue to use the symbol delta y. The wording of the problem implies that the objects begin at rest, so v initial y is 0. For v final y, we could use the slightly more specific symbol v sub 1y. For a sub y, we can substitute the result that we determined from our Newton's second law equations, positive 2.45 meters per second squared. Remember that our plan all along was to use a sub y as the connecting link between Newton's second law and kinematics. We've now completed the kinematics setup. The purpose of the kinematics setup is to organize the kinematics data, much like the purpose of the force tables is to organize the force data. Make it a habit to write down the kinematics setup for every kinematics problem you work on. Here are the steps we completed for the kinematics setup. When you know values for 3 kinematics variables, you're ready to choose a kinematics equation. We do know 3 kinematics values, delta t, v initial y, and a sub y. So we're ready to choose a kinematics equation. The quickest way to choose a kinematics equation is to ask, which kinematics variable do we not care about? We care about these 3 variables because we know values for them. We care about delta y because that's what we need to figure out in order to answer the question. So for this problem, the one kinematics variable that we don't particularly care about is v final y. So let's choose the kinematics equation that's missing v final y. Remember that for this problem we've decided that we're dealing with constant acceleration with changing velocity. So we choose from the kinematics equations for constant acceleration with changing velocity. Remember that for this problem we're applying kinematics to the y component. So we choose from the kinematics equations for the y component. We choose the kinematics equation that's missing v final y. That's this equation. Begin by writing the general equation. Delta y equals v initial y delta t plus 1/2 a sub y delta t squared. Next, we plug specifics into the equation. The kinematics equation now has one unknown remaining, so we can solve this equation for delta y. Our result is that delta y equals positive 2.76 meters. If there's enough room on your paper, arrange your Newton's second law equations and your kinematics work in adjacent columns, like we've shown here. that will help you to keep your math organized. We should build our result for delta y into our sketch. Our result for the delta y for mass 1 is positive. Our positive y direction for mass 1 is up. So, our result for the delta y for mass 1 tells us that during the 1.5 second interval between t sub 0 and t sub 1, mass 1 rises a distance of 2.76 meters. We build that information into the sketch, like so. Because they're connected by the rope, the distance that mass 2 falls is equal to the distance that mass 1 rises. So, during the 1.5 second interval, mass 2 falls a distance of 2.76 meters. Build that information into the sketch. Our sketch now makes it clear that after 1.5 seconds have elapsed, the difference in heights of the two masses is 2.76 meters plus 2.76 meters, which equals 5.52 meters. Remember, for a kinematics problem, make an effort to draw a large, neat, clear sketch and to build as much information as possible into the sketch, as we've illustrated here. Now we're ready to answer the question. The difference in height after 1.5 seconds is 5.5 meters. Here's a summary of the final steps that we completed in our kinematics process. Actually, we have one more check left to make. We should check that our results make sense. Does it make sense that our results for a1y and for a2y are both positive? The positive direction for mass 1 is up, and the positive direction for mass 2 is down. So a sub 1 points up and a sub 2 points down, as I've drawn in the sketch. Do these directions for the acceleration vectors make sense? In general, the direction of the acceleration vector doesn't indicate the object's direction of motion. But if an object starts from rest, like the objects do in this problem, then the direction of the acceleration vector does indicate what direction the object will begin moving. Because object 2 has a greater mass than object 1, we expected mass 2 to begin moving down and mass 1 to begin moving up. So yes, the directions for our acceleration vectors do make sense. Does the magnitude of our result for the acceleration make sense? For this problem, it's interesting to compare our result for the magnitude of the acceleration with 9.8 meters per second squared, which is the magnitude of freefall acceleration. Because mass 2 is being held back by the rope, rather than falling freely, we would expect mass 2 to fall with an acceleration that is smaller in magnitude than the magnitude of freefall acceleration. So yes, our result for the magnitude of the acceleration does make sense. Does it make sense that our result for the delta y for mass 1 is positive? The positive direction for mass 1 is up, so our result indicates that mass 1 is being displaced upward. Again, we expected that mass 1 would move upward, so yes, it does make sense that our result for the delta y for mass 1 is positive. In our solution, we used this equation. We used this rule to justify the equation. Now, in this part of the video, I want to demonstrate that this rule really is correct. And furthermore, I want to show you that the rule only works when we choose a positive direction for each object that points in the direction of motion for that object. In general, the direction of the acceleration vector does not indicate the object's direction of motion. But if an object starts from rest, then the direction of the acceleration vector does indicate what direction the object will begin moving. In this problem, the objects begin at rest, and then we expect that mass 1 will begin moving up, while mass 2 will begin moving down. So in this problem, we expect that a sub 1 will point up and that a sub 2 will point down. So a sub 1 will point in the positive y direction we've chosen for mass 1. So a sub 1y will be positive. And a sub 2 will point in the positive y direction we've chosen for mass 2. So, a sub 2y will also be positive. Because they're connected by the rope, the magnitude of the acceleration will be the same for both objects. So we can represent the magnitude of the acceleration for both objects with the same symbol, a, written without an arrow on top. So, a sub 1y equals positive a, and a sub 2y also equals positive a. So we see that a sub 1y really does equal a sub 2y. So we've confirmed that this rule really does work for this problem. This confirms that we were correct to use the equation a1y equals a2y in our solution for the problem. Now, what would happen if we had chosen up as the positive y direction for both objects? In that case, a sub 2 would still point down. But now, down would represent the negative y direction for mass 2. So a sub 2y would be negative. In this example, we haven't changed anything for mass 1, so a sub 1y will still be positive. Because they're connected by the rope, the magnitude of the acceleration will still be the same for both objects. So we can still represent the magnitude of the acceleration with the same symbol, a. So in this case, a sub 2y would equal negative a. So if we choose up as the positive y direction for both objects, a sub 1y does not equal a sub 2y. Instead, a sub 1y equals negative a sub 2y. This example confirms that this rule only works if we choose a positive direction for each object that points in the direction of motion for that object. So you can see that it was best to choose the direction of motion for mass 2, down, as the positive y direction for mass 2, to avoid having to deal with this negative sign. Now let's do a recap of our work on this problem. Based on the concepts that were mentioned in the problem, we expected to apply both Newton's second law and general one-dimensional kinematics to solve the problem. If there's enough room on your paper, arrange your Newton's second law equations and your kinematics work in adjacent columns. It simplified our solution to choose the direction of motion for each object as the positive direction for that object. For this problem, that meant choosing different y-axes for mass 1 and for mass 2. The magnitude of the tension force was the same at both ends of the rope, so we used the same symbol, capital T, to represent the magnitude of the tension force at both ends of the rope. Since we did choose different y-axes for the two masses, we had to be extra careful to get the correct plus and minus signs for every component in our force table. Because we chose a positive direction for each object that points in the direction of motion for that object, we could use this rule to write the equation a sub 1y equals a sub 2y. And then we could use this equation to substitute a1y in for a2y in this equation. But if you choose up as the positive y direction for both objects, then a sub 1y will not equal a sub 2y. We obtained a system of two equations in two unknowns. For the particular equations that we obtained, the most convenient way to solve the system of equations was the addition method. For a kinematics problem, organize the kinematics data with a list of the 5 general kinematics variables, like this. Underneath your list of the general kinematics variables, write the specific numbers and symbols that apply for the problem. Use acceleration as the connecting link between Newton's second law and kinematics. For a kinematics problem, build as much kinematics information as possible into your sketch. When possible, build the question into the sketch. Draw a large sketch so that there's enough room to clearly build all the necessary information into the sketch. The wording of the problem implied that the objects began moving from rest, so the initial y is 0. To succeed in physics, think in terms of components, and always try to use the exact right symbols, including the exact right subscripts. In this problem, the objects were moving only in the y component, so we applied kinematics to the y component. So, in our kinematics setup, we wrote the symbols specifically for the y component. We wrote delta y rather than delta x, and we included y subscripts for velocity and acceleration components. We used y subscripts to emphasize that for this problem, both of our Newton's second law equations referred to the y component. We used 1 and 2 subscripts to carefully distinguish symbols that referred to mass 1, like W sub 1 and M sub 1, from symbols that referred to mass 2, like W sub 2 and M sub 2. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.